Hello. So in the previous video, we have seen that when we are dealing with normal subgroups, cosets will be involved. Okay, we even have the theorem that says that H, which is a subgroup in G, it will be normal if and only if every left coset is a right coset. So cosets will be very much involved in normal subgroups. And this is actually a theorem that you have done in the previous semester, which states like this. If H is a subgroup of G, then H, small h, is equal to capital H if small h is an element of H. I won't be doing the proof for this one because you have already done in the previous semester, but this is very much useful. Always remember that if small h belongs to capital H, then you will always have this. It's like h, small h can be absorbed by this capital H. So again, if you have something like this, if x belongs to H, again, I repeat, okay, this small h, it is just a notation. It can be anything. Okay, it is just used to represent an arbitrary element of capital H. So if x belongs to H, even if you have x, then and H is a subgroup, of course, then Hx will be equal to H. Okay, so once again I repeat, even if you have x belongs to H, Hx, then the next line will be equal to H. Okay, x will be absorbed by H, provided small x belongs to H. And this works not only for small letters, it even works for big letters. What I mean by that, even if you have, if H is a subgroup and H occurs together like this, they can be combined to form only one single H. Okay, so the idea is the same. Okay, again, I won't be doing the proof for this because you have already done it in the previous semester. And also one thing that maybe it's very much useful if I mentioned it here is, if you suppose you have a set like this, xyz, how does an element of xyz looks like? Okay, an element of xyz will look like this. Maybe it will look like a, it is an element a such that a can be written as x y z. But we don't know what x is, y and z is, but we just know that x will belong to x, y belong to y, and z belongs to capital Z. So even if you have maybe another set like this, and a, h, b, y, z, so how will we denote an element of this? Okay, this will of course be a set x such that x equal, instead of capital we will replace it with the small letters. The small letters will keep it as it is, h, b, y, z. Okay, a, they are already given elements. Okay, so that is why small n belongs to capital N, small h belongs to capital H, and similarly this one, z, belongs to capital Z. Again, okay, maybe another example for this one is required. Even if you have something like this, I will just erase this one. But what if two big letters repeat? Okay, if you have maybe Na, Nb, NCH. All right, it's looking like a chemical formula of some compound. Okay, but it's not it. Okay, so if you have to represent an element of this one, it will look like this. Now we have to be very careful. Some of you may be thinking that we can write this one as Na, Nb, Nc, and small h. Okay, small n belongs to n, small n belongs to capital N, small n belongs to capital N, small h belongs to capital H. But over here we have to be very careful. Even though it is the same set n everywhere, but once you write it in element wise, okay, the elements, they may be different. That is why we will be writing n1, n2, n3. All right, so over here n1 belongs to n, n2 belongs to n, and n3 belongs to n. So you have to be very careful if the same big letter occurs more than once, you have to use maybe subscript like this n1, n2, n3, and so on. Similarly, if for h, okay, you can do the same. Okay, with that being said, okay, let us learn this new theorem, theorem 3. We have done theorem 1 and theorem 2 for normal subgroups. This is theorem 3. Okay, so the theorem states like this: let H be a subgroup of G. H is normal in G if and only if product of two right cosets is a right coset. Again, we have this word if and only if, so the proof will contain two parts: the direct way and the converse. All right, so the direct way first. Okay, let the product of two right cosets be a right coset. What do we have to do? We have to show that H is normal in G. Okay, so since we are given that the product of two right cosets is a right coset, so that is what I've written. Let the product, this one is it is a right coset, this one it is a right coset, let it be equal to a right coset. We are given just that. Product of two right cosets is a right coset, so that is what I've written. Product of right cosets is a right coset. And H, we have to show that H is normal in G. So what do we actually expect this value of X to be? Okay, eventually this value of X, it will be equal to AB. Okay, maybe in better way I will say that eventually you will have that this HX will be equal to HAB. Okay, but we need a proof for that. Okay, so this is what I will do. All right, so an element of HAHB, an element of HAHB, it will look like this. We have done a similar thing like this in theorem 2. An element of H, an element of this set will be in this way: H1A, H2B. Okay, but we can take particular values for H1 and H2 also. It will still be in the set HA, HB. Okay, so instead of H1, I can take a very shear element that is in capital H, that is E. E, A, E, B. This one belongs to H, A, H, B. It belongs to H, A, H, B because the identity element is in H. Similarly, this identity element is in H. Okay, so over here we are using the same element, but sometimes we have to use different elements that belongs to H. But over here, the same element, that is the identity element, it will work. Okay, so EAEB, E you combine with A, you will get A. E combined with B, you will get B. So AB belongs to HA, HB. But HA, HB, it's equal to HX. So AB belongs to HX. We will denote this one as equation 1. The reason for this one is since HA, HB equal HX. Okay, but also AB it can be written as EAB. Okay, so this one it can be written as it belongs to HAB. Okay, the reason is since E belongs to H. Okay, so this one is equation 2. From 1 and 2, from 1 and 2, just say AB belongs to HX, belongs to HAB. AB belongs to HX intersection HAB. So there is an element that is contained in the intersection. So we can immediately write down HX intersection HAB is non-empty. And because they are cosets, you can see this one, it is a coset. This one is again a coset. So that is why HX will be equal HAB. Once the intersection of two cosets, of two right cosets is non-empty, they will be equal. Okay, so we will have this. Hence, HA, HB, it will be equal to HAB. A and B, they are elements of G, so for all A and B belongs to G. Therefore, even if A, you replace it by G, and B, you replace it by G inverse, they are still elements of G. This equation, it works for all elements of G. So even if you replace it by G and G inverse, which belongs to G, okay, we will have HG inverse equal HG inverse. This one you cannot move around, okay, but this one you can combine. G and G inverse will form the identity E, okay, so you will get H. So you will have this. All right, so now that we have got this, what can we say? And what can we say? Hence, if G belongs to G and H belongs to H, we have, what do we have? Maybe call this one equation 3. Okay, we have E, G, H, G inverse. E, H, G inverse, it belongs to H, G, H, G inverse. The reason for this one is because E, it belongs to H, G, it's just G only. This small h, it belongs to capital H. So we will have this line. But from equation 3, this E, you can remove it. From equation 3, we will have GH, G inverse belongs to H. So once you have this one, so from 4, okay, so once you have equation 4, hence H is a normal subgroup. It is a normal subgroup because it is already a subgroup that is given in the statement of the theorem. And also we have this normal condition GH, G inverse belongs to H for G belongs to G and H belongs to H. Hence, H is a normal subgroup. I hope it is clear. So that is how we prove the first part. That is, if the product of two right cosets is a right coset, we can get that H is normal in G. Okay, now the converse. The converse is, let H be normal in G to show product of two right cosets is a right cosets. Two right coset of H is a right coset. So how will we do this? We just state that HA and HB be two right cosets of H, right cosets of H in G. So we need to show that the product, it is again a right coset, so HA, HB. But because H is normal, this one, if you can write this one, it is the product of the two right cosets. You can write it down like this. But because H is normal by theorem by theorem 2, you have that left coset it is a right coset. This one, it is a left coset, so it is a right coset, since because H is normal, every left coset, the reason for this one is this: every left coset is a right coset if H is normal. This is by theorem 2. So we will have this. So if you expand, okay, remove the brackets, you will have like this. Again, H occurs together, they can be combined to form a single capital H. So we'll have this. So we have got that the product of two right cosets, it is now a right coset. Hence we are done. Okay, so this is the end of the proof. All right, so this is the end of the proof. These three theorems, they are very important, okay, because if we have to prove that H is normal in G, we can either use theorem 1, we can either use theorem 2, or we can use theorem 3. Okay, so it gives us three different ways to prove that a subgroup is normal. If you combine with the definition, that gives us 4 ways. So we now have 4 ways to prove that a subgroup is normal. We can either use the definition, theorem 1, theorem 2, or this theorem 3. Okay, so they are very, very important. Uh, with the theorems being done, okay, now let us do an exercise. This is an exercise. This is actually a very good exercise for you to try out, but I will do it just for you to be more familiar on how do we prove that subgroups are normal. Okay, so let's see. The exercise is this: let H be a normal subgroup of G, let K also be a normal subgroup of G, then H intersection K is a normal subgroup of G. Okay, so we need to prove that the intersection of two normal subgroups is again a normal subgroup. So how will we do it? Okay, the first part is proving. You have to prove that H intersection K is a normal subgroup. So what will we do? The first part is proving H intersection K is a subgroup. Again, if you have to prove that it is a subgroup, we have the three conditions. The first one is proving. I think it is best if I just write down it down directly. The first condition, that is condition A, we have H intersection K, it will be a subset of H. It will be a subset of H. It will also be a subset of G. The reason for this one, H is a subset of G because H is a subgroup. That is what is given. H is a subgroup of G, so first of all, it has to be a subset. That is why. Okay, moreover, E, the identity element is always in any subgroup. E belongs to H. Also, E belongs to K. Therefore, H intersection K is non-empty. Okay, because E belongs to H, E belongs to K, so E belongs to H intersection K. So that's why the intersection is non-empty. So condition A is done. H intersection K it is a subset. Moreover, it is a non-empty subset. So condition A is done. B. Condition B is we have to get proving AB belongs to H intersection K for all A, comma B belongs to H intersection K. So how will we do this? Since let A, comma B belongs to H intersection K. So what can we say? We can say that A belongs to H, A belongs to K, also B belongs to H, B belongs to K. If A belongs to H and B belongs to H, because H is a subgroup, so we can write down AB belongs to H. Maybe equation 1, since H is a subgroup of G. This first part actually you have done it in the previous semester as well. Also what can we have? A belongs to K, B belongs to K, so AB belongs to K. Call this one as equation 2. Again, the reason for this one is since K is a subgroup. So from 1 and 2, we have AB belongs to H intersection K. AB belongs to H and AB belongs to K. So we will have AB belongs to H intersection K. Okay, so condition B is done. Now we will do condition C, proving A inverse belongs to H intersection K for all A belongs to H intersection K. So how will we prove this? Let A belongs to H intersection K. We will have A belongs to H and A belongs to K. Ultimately, we will have A inverse belongs to H because H is a subgroup. The inverse of an element, it belongs to a subgroup. Okay, the inverse of an element of a subgroup, it belongs to that subgroup. So similarly for this one, A inverse belongs to K. The reason for this, H, K are subgroups. So we'll have this. So ultimately we will have A inverse belongs to H intersection K. So with the condition A, B and C being satisfied by H intersection K, we can conclude that hence H intersection K, it is a subgroup of G. Now the second part of the proof is just to prove that H intersection K, it is normal. That is, we have to prove the normal condition for H intersection K. Proving G H intersection K, G inverse, G, maybe I will denote it by X, okay, because we are having H and K, all right, and we cannot use H, otherwise we will be confused. You will think that small h belongs to capital H. So over here I'm using small x, proving GXG inverse belongs to H intersection K for all G belongs to G and X belongs to H intersection K. Okay, so again over here I will repeat, if you have to show that H intersection K is normal, you have to show this: GXG inverse belongs to H intersection K. G doesn't matter too much, it will belong to G, and X belongs to H intersection K. Okay, this from here. Alright, so how will we do it? We will start with this. Let G belongs to G and X belongs to H intersection K. Let G belongs to G, X belongs to H intersection K. So over here we can say X belongs to H and X belongs to K. So G belongs to G, X belongs to H. What can we say? G inverse belongs to H and GX, G inverse belongs to K. This is the reason for this one being that H and K are normal subgroups. If H and K are normal subgroups, so they also satisfy the normal condition. You see this one. X is in H. X is in H, then GXG inverse will belong to H. Similarly, X belongs to K, so GXG inverse belongs to K. That only works for normal subgroups. So that's why the reason is H and K are normal subgroups. So ultimately we will have GXG inverse belongs to H intersection K. So this proves a normal condition for H intersection K. So hence this is the end of the proof. H intersection K, it is a normal subgroup of G. I think this is enough for today.